Okay, so let us come back. Okay, so let us come back and let us come back to the real lectures for the material. Okay, so now today I'm going to just start to talk about the basics of differential equations. Okay, so let me open the lecture notes. Okay, so let me open the lecture notes in just one moment. Okay, so let me open the lecture notes and yeah, so let's start the real lecture for this course. Okay, so today I'm going to talk about the basics of okay, so today I'm going to talk about the very basics of uh, differential equations. Okay, so here you can see this is the how my lecture notes are going to look like. Okay, so and these lecture notes are directed directly to answering those questions that you might have on the exams of this course. So they are very important, and I suggest you look at them and make full use of this lecture notes. Okay, so now let me start everything. Okay, so we are going to talk about differential equations. Okay, so I think okay, so I think you will have okay. So I think we will. Okay, so I think everybody in this lecture. So let me write here. So this is the way we're going to record the lectures. There will be this lecture notes written on this Microsoft OneNote. Okay, so and but there will be also accompanied with the lecture notes. Okay, so today our course is about elementary. Okay, so let's say elementary differential equations. Okay, so differential equations. Okay, so this is the title of this course. Okay, so and I think everybody in this lecture has already taken has already taken a class on differential I mean the calculus, right? So everybody in this lecture has entered this calculus classes, right? So in calculus classes, you have been experiencing notions like integral, differentials. Okay, so uh, differentials and as well as integrals, right? So differentials and integrals, right? So the differential equations is kind of, in a certain sense, is a continuation of our course on calculus. Okay, so and it will make full use of calculus. Okay, so it will make full use of calculus that you have been learning in the previous semesters of when you are staying at this university. Okay, so and so that will be that will be like the very the general scope of this class. Okay, but when we talk about differential equations, what is a derivative, right? So the differentials are related to derivatives, right? So they are related to derivatives, right? So derivatives. So what does the derivatives mean, right? So in your calculus classes, right? So what does the derivatives mean in your calculus classes, right? So by derivative, it means that I give you a function f of x, right? So I give you a function f of x. Suppose the function f of x has a graph. So this is the graph of this function, right? So and if you take a point x, and what's the derivative f prime of x? In order to have f prime of x, you just have to draw a tangent line, right? So at point x, tangent to the graph of this function, then you're going to the slope. All right, so the slope of this tangent line is going to be called f prime of x, right? So the slope is f prime of x. Okay, so that's kind of a slope, right? So the derivative is actually a slope, right? So and another way to explain the derivative is through the rate of change, right? So that means if you treat fx as a quantity, then the f prime of x, as we have seen in calculus, it is the limit as epsilon goes to 0 of f of x plus epsilon minus the f of x divided by epsilon. So what does this mean? It means the rate change, like if x changes by an epsilon, what is the change of f compared to the change of x? So that means this is actually a delta f over delta of x as the limit as the delta x go to 0. So that means sometimes we write it as df over dx if you use Newton's infinitesimal notions, right? So the df over dx, right? So that's kind of the thing, right? So it can be described as a rate of change of a certain quantity, right? And this rate of change is usually related to physical interpretations. Okay, so it's usually related to physical interpretation. For example, such physical quantities as the speed can be written as a v into ds over dt is the rate per rate change of time, right? So ds over dt, right? So that's the speed, right? So and besides the speed, there's another notion which we sometimes call it the acceleration, right? So and what's the acceleration, right? So what's the acceleration? Well, the acceleration is going to be okay. So the acceleration is going to be such quantity. So this acceleration, right? So the acceleration is going to be the quantity a, which is the dv over dt, is the per rate change in time of the speed, and which can be written as d square s dt square, right? So that's the acceleration, right? So the speed, acceleration, right? So that's our kind of all the things about this rate of change. Okay, so rate of change. Now, what do we get? Okay, so what's the differential equations, right? So far, our explanation kind of tells us what it means. What does it mean by differentials or derivatives, right? So now, if you look at the course title, right? So the course title is called a differential elementary differential equations. Okay, so it's called elementary differential equations. So that means we have to consider not just the differentials, but the equations relating those differentials. Okay, so but the equations relating those differentials. So what does a differential equation mean? Okay, so the differential equation means that you have a law or principle underlying the real world problem. Okay, so that means you're going to relate the rates. Okay, so the rates, or as I just said, differentials can represent the rate of change of certain quantity. Okay, so differentials can represent the rate of change of certain quantity. Okay, so that means we are going to have these equations of the rates. Okay, so equations of the rates. And so that's once you have all the rates of certain quantities, we're going to ask what's the relationship between the derivatives and the laws or principles underlying the real world problems. Okay, so here we come to the definition of a differential equation. By a differential equation, it means an equation that contains derivatives. These are called differential equations. Any equation that contains derivatives are called differential equations. Okay, so but it might be too abstract to talk about it, right? So too abstract to talk about it in terms of such a definition, right? So it might be too abstract to talk about it in terms of such a definition. But here I would like to show you a real-world example from medical sciences. Okay, so I'd like to show you a real-world example from medical sciences. Okay, so what does this example say? Okay, so it says that if you have a certain drug, okay, so a certain drug is being administered intravenously to a hospital patient. Okay, so the fluid containing 5 milligrams per cubic centimeters of the drug enters the patient's bloodstream at a rate. Okay, so remember here there's a word rate, which means that you must have some differentials. Okay, so at a rate of 100 cubic centimeters per hour, the drug is absorbed by body tissues and otherwise leaves the bloodstream at a rate proportional to the amount present, with a rate constant of 0.4 per hour. Okay, so here you can see that there are always these words about the rates, right? So they are going to be called the rates. Okay, so and the rates are essentially those is going to be are essentially going to be related to okay, so are essentially going to be related to differentials, right? So that we're going to use these rates and okay, so we're going to use these rates and record a differential equation. Okay, so now let's see the questions. Okay, the questions are: first question, assuming that the drug is always uniformly distributed throughout the bloodstream, can you write a differential equation for the amount of the drug that's present in the bloodstream at any time? Okay, so and part B of the question: how much of the drug is present in the bloodstream after a long time? Okay, so now how do we solve this question? Okay, how do we solve this problem? Well, here you can see that the description of the problem is about, the question is about how much drug, right? So amount of the drug present in the bloodstream. So in order to do that, okay, so the example, okay, so bloodstream, okay, so bloodstream drug problem. Okay, so how do you do that? So you are going to assume that the amount of drug in the person's bloodstream, so amount of drug at time t in bloodstream, right? So the amount of drug at time t in the bloodstream, right? So let's say suppose this amount is denoted by A of t. Then you look at the problem, right? So then you look at the problem. What does this problem say? So the problem says that you have fluid entering containing 5 milligrams per cubic centimeters, right? So enters the patients at a rate of 100, right? So what does that mean? Well, that means we have the rate. So that means let's say the per unit time change. So that's the rate of change, net rate of change of the amount of drug is going to be characterized by two quantities, right? So now we're going to have the inflow, net rate change of the amount of drug is going to be the inflow minus the outflow, right? So that's where's the inflow? Well, the inflow is going to be the fluid enters the bloodstream. So that's 100 centimeters per hour is the rate, and then containing 5 milligrams. So in terms of the amount of drug, is 100 multiplied by 5. So you have to use the concentration multiplied by the per unit time volume, right? So that's the inflow. Okay, so that's the inflow of the drug. What's the net rate outflow? Well, the outflow says that you are going to the body. Okay, so the body of the patient is going to absorb these body tissues are going to absorb the drug, right? So the rate is proportional to the present amount with a rate constant of 0.4. So that means, let's say first of all, there has to be a minus sign in front of the outflow because this is the outflow. So that means this is going to characterize how much drug is being absorbed. So there's a minus sign, and the rate constant is 0.4 multiplied by the amount of drug, A, right? So 0.4 multiplied by the amount. So this is actually a differential equation. Okay, so how is this a differential equation? Well, the left-hand side of this equation contains derivatives, right? So, I mean, it is okay that the right-hand side also contains derivatives, but here, for this practical problem, the right-hand side of this equation does not contain a derivative. But indeed, I mean, even the left-hand side has a derivative. This is a differential equation. Okay, so this is a differential equation. So that's an equation that involves an unknown quantity as a function of time. Okay, so and we're going to call it the amount of drug, and this amount of drug satisfies such a differential equation. Okay, so this is a typical example of a differential equation. Okay, so here we said, and can you write a differential equation at any time, right? So that's this differential equation. Okay, so now let me, so this is kind of going to just give you, okay, so this is kind of going to just give you, okay, so an idea of what is a differential equation. Okay, so just give you an idea what is a differential equation. Okay, so how it can be something that involves derivatives, right? So it can be an equation that involves derivatives, which is being characterized by certain rate changes. Okay, so by certain rates of this of the quantity. Okay, so that's a differential equation. Okay, so now let's look at the second problem. Okay, so what does the second problem say? Okay, so second problem says how much of the drug is present in the bloodstream after long time, right? So what is going to happen after long time, right? So what's going to happen after long time? If you look at this differential equation, let me rewrite it here. Okay, so is dA over dt is equal to, okay, so it is equal to 500, right? So minus 0.4 of A. So I'm going to ask, like, how much of the drug is going to remain in the bloodstream? AT is going to converge to something as t goes to infinity. If the time is long enough, okay, so if you run the system for long enough time, what's the amount of drug remained in the person's bloodstream, right? So what's the amount of drug remains in the person's bloodstream? So what's going to happen in this problem? Well, it looks like we don't know how to solve this differential equation. That's the problem, right? Why is that the case? Well, imagine that you don't have this term. So let me say, okay, so let me use red ink. Okay, so imagine that you don't have this term, right? So the equation is going to be just the dA over dt is going to be 500. In this way, you are able to solve it because you are going to see that A of t is just 500t maybe plus a constant, right? So that's easy to solve because the right-hand side does not involve A. Okay, so no A. But in general, a differential equation should look like something like this. Okay, a right way to have this differential equation is to have something like this, that both on the left-hand side of this equation as well as the right-hand side of the equation are going to have the same quantity A, which you don't know. Okay, so the unknown quantity appears both on the left-hand side and the right-hand side of this equation. So that kind of gives us a trouble because in this case, we don't know really how to solve such differential equation because it's both the left-hand side and right-hand side contains the unknown constants, right? So the unknown quantity. So it's hard. Okay, so but how do you read some quantity from this equation? Well, if t goes to infinity, right? So imagine the real world problem. You're being administered, a certain drug is being administered into your body, right? So and you're going to consume this drug. After a long time, are this amount of drug going to accumulate in your bloodstream by time? It won't, right? Because at some moment it will reach a steady situation. Because if it continues to grow steadily, then your bloodstream your bloodstream are not going to tolerate such amount of concentration of drug. So it will reach a certain equilibrium, right? So and what does this equilibrium mean? The equilibrium means that AT is going to be some kind of constant A, right? So A infinity, right? So that's going to be, let me say, is abbreviated as A. So what is A infinity? Can you calculate A infinity? Well, it doesn't matter because no matter which AT satisfies this equation, if AT converges constant, it means that at the infinity, the derivative will be zero because it converges to a constant. And therefore, as 500 minus 0.4 of A infinity, right? So it's a 500 minus 0.4 of A infinity, right? So 0.4 of A infinity. Now that means, okay, so that means you're going to calculate A infinity. Okay, so A infinity is 500 divided by 0.4, which is 5,000 divided by 4, so that's kind of a 1250 mg, because our measurement unit is mg. So that's kind of a nice way to calculate the final amount, right? So let's say the final amount or the steady state amount of the amount of drug in the bloodstream, right? So the amount of drug in the bloodstream. Okay, so that's A infinity. Okay, so let's look at this problem, right? It looks like we have everything about it, right? So the A infinity is also calculated. So that's important, right? So as you can see that we have to describe a certain dynamics, right? So a certain dynamics, that means something is evolving in time. Okay, so that means something is evolving in time. Something is evolving in time from some quantity is evolving in time with respect to time, and it changes by time. Okay, so it changes by time, right? So it changes by time, and the description is about how this quantity changes by time. Okay, how this quantity changes by time. Okay, so and this is described by a certain kind of differential equation. Okay, so here you can see from all our descriptions. You can see that we're using differential. The reason why you are always requested to take differential equation class is because differential equations. Okay, so it's because differential equations is a fundamental way of doing mathematical modeling. Okay, so right, so it's a fundamental way of doing mathematical modeling. By mathematical modeling, it means that you're using a kind of qualitative way to predict the future, right? So in the real world problems, right? So in order to solve any real world problem, if you want to use mathematics, you have to use the past data, all right? So existing data to predict something, some kind of new data that you don't want to, you don't have access to, but you want to know. For example, the amount of drug in the person's bloodstream. So that's a mathematical modeling. Okay, so this is why this course is very important for engineer students like you, because essentially engineering is nothing but a way of doing mathematical modeling, right? So you're using mathematical methods to model your real world problems and solve them. That's called engineering, right? So that's kind of the thing. Okay, so and you can see from our drug example that the fundamental steps of mathematical modeling consists of several steps. Okay, so the step one is to find the principle or the law underlying the given problem, right? So for example, here in our drug problem, the very basic principle is the net rate change is the net rate inflow minus the net rate outflow, right? So inflow minus outflow is the net rate change. So that's the principle of the law underlying the given problem. Okay, so these principles or laws are essentially non-mathematical. Okay, so they're physical or belonging to natural or even social sciences. For example, in economics, a lot of principles are described by differential equations, right? So this is about the laws underlying the problem. And the second step is to decide the variables and parameters. Okay, so decide the variables and parameters. For example, by variable, it means the quantity that you don't know. For example, here in our differential equation, the variable is a, right? So that's a, or we may say the function, right? So it's the a is the unknown function, right? So what are the parameters? Well, the parameters are t, right? So or you can say t is a variable. It doesn't quite matter about the meaning of variables and parameters. It just says that you are going to have an equation that one quantity is a function of another quantity. And we describe this unknown function into an equation that involves the derivative of that function. This is called a differential equation. Okay, so that means you have to decide the variables and the parameters, right? So decide the variables and the parameters. Now the third step of the modeling is to rewrite the principle or the law into a differential equation. That means you're going to use the underlying physics or mathematical formulas you know to express each term. Okay, so to express each term with the variables and parameters, and then you're going to plug in this equation. Okay, so you're going to plug in that equation into the equation, and that will give you a differential equation. Okay, so that's kind of how do we model a differential equation. Okay, so that's kind of the thing. How do we model a differential equation? Okay, so how do we model a differential equation? Okay, so that's probably let me see. Okay, so let me see the time. Okay, so that's probably all I want to say for today's lecture. Okay, so that's probably all I want to say for today's lecture. Okay, so I apologize for the problem that we had for today, but we did have a remedy to that problem, namely by recording the lectures on Panopto. Okay, so you should be able to see it whenever it's available on Panopto. I'll be working on this. Okay, so I hope to see you on Wednesday, just at 9 o'clock. And by that time, I wish Zoom has already fixed all his problems and come to ordinary use. Okay, so let's meet on Friday, on Wednesday to continue our lectures. Okay, so see you on Wednesday.